Hey, welcome to the podcast on solving trigonometric equations. So, it says using arc functions. Let's kind of explore why that is with a really simple trigonometric equation here. Cosine x equals negative zero point 0.7. So, let me just remind you, I realize this is kind of silly, but what does it mean when we say solve this equation? What solving an equation means is finding the values of the variable that make the equation true. And in this case, the variable is x. So find the values of x that make this equation true. Okay, so if I think about this, and I think about how trig functions work, right? Cosine of something equals negative zero point 0.7. So I'm looking for angles, right? Because angles are what I take the cosine of. So what angles have a cosine value of negative zero point 0.7? This should be ringing a little bit of a bell from yesterday, right? Or when you watch the vodcast on arc functions. What arc functions do is they find all of the angles that have a cosine of a particular value or a sine of a particular value or a tangent of a particular value, right? They're finding all of the angles that meet the criteria that I have. Um, so let's kind of think about this graphically for a second. Looking at this graph. So so this is a graph of cosine x. Oops, that's not what I meant to do. Let's try that again. Y equals cosine x. And you can tell it's in radians, right? Because these numbers are weird. It's not labeled in terms of pi, but you can tell that the numbers are involving pi and that the half period is pi and the whole period is 2 pi. So this is just y equals cosine x, which is exactly what I wanted to think about. So I'm thinking about when is the cosine value equal to negative zero point 0.7, right? So negative zero point 0.7, graphically, it's maybe, I don't know, right here, negative zero point 0.7. So where is cosine equal to negative zero point 0.7? And you can tell that there are lots of different places where that's true. And if I were to zoom out and look at more of this graph, there would be more values at which cosine of x is equal to negative zero point 0.7. So there's lots of different answers. Okay, so let's think about this. I want to find all the values of x that have a cosine of negative zero point 0.7. So what that just is x is equal to arc cosine of negative zero point 0.7. So one of the ways that I can think about getting from the initial problem here to this line here is what I'm doing is I'm inverting the cosine function, right? When I'm solving equations, the way that I think about it is I do inverse operations on both sides of the equal sign in order to uncover the x. And that's really what I'm doing here is I'm undoing the cosine here by doing arc cosine to both sides, basically. Um, so then all I have to do is evaluate arc cosine, right? Remembering what I did before, I'm going to draw my little picture because I always do that when I'm evaluating one of these arc functions because it's really going to, that was a terrible unit circle, but okay. Um, it's going to help me think about what's going on. Where is cosine equal to negative zero point 0.7, right? Cosine on the unit circle is u. Here is negative zero point 0.7. It's about here, right? So here are the two places on my unit circle in their angles that have a cosine of negative zero point 0.7. I find one of those particular angles by doing inverse cosine of negative zero point 0.7, which I will do right now by pulling up my calculator, whoa, which maybe is a little bit slower than I had hoped. Okay, there it is, right? So inverse cosine of negative zero point 0.7. Oh, that looks like degrees, but I'm in radians, so let me change my mode. Second quit and second enter to just type that in again. Great. I get 2.346 radians. Right, 2.346 radians. And that tells me that this other one by symmetry is negative 2.346 radians, right? So x is equal to plus or minus 2.346 plus 2 pi n radians, right? Because this point here is 2.346 plus 2 pi n, and this point here is negative 2.346 plus 2 pi n. Let's just think about how this goes on the graph, right? Plus or minus 2.346. Well, so 2.346 is probably this point here, 2.346. Right here is negative 2.346, 2.346. Now look at this. Look at the shape of the graph, right? There are two solutions in each period of cosine, right? There's the solution when it's on the way down before it gets to the minimum, and then there's a solution on the way back up. And 2.346 gives you the point that's on the way down, and negative 2.346 gives you the point that's on the way back up, right? So what is this point going to be here, right? Well, that is a whole cycle less than 2.346. So that is 2.346 minus 2 pi. And this one here is a whole cycle more than negative 2.346, with negative 2.346 plus 2 pi, right? So I can totally think about this graphically in addition to thinking about it with the arc cosine business that I had before. Okay, let's go on to a little bit of a more challenging example than this one that we looked at right now. Okay, so now I have a little bit of a more complex equation. Oh, hang on a second. Sorry, pause it for a second there because there's a typo in this equation. Okay, so this is certainly a more complex trigonometric equation than the one that we had before. It uses the variable theta, which remember we're going to use as a guide to tell us that this is a degree problem and not a radians problem. So really what's going on here is that I have this complex sinusoid, right, that has all four transformations, and I want to figure out what angles for which the sinusoid is equal to 3, which I think is another typo. Hang on one second. Okay, negative 3. That was really what I wanted to do. And you can actually tell that 3 was not really possible, right? Because if I look at this equation, the sinusoidal axis is negative 5. It goes up and down 3 from there. So it really would never get to 3, right? Because the highest this graph got was negative 2. Okay, so how do I go about solving this equation? So really the first thing that I want to do is I want to isolate the sine function. And you have to remember that there's the things that are going on in the argument of the sine function, and there's things that are going on outside the argument of the sine function. And really, I want to make sure that I never cross what's inside the sine and what's outside the sine, that I always think about them as completely separate types of functions. For instance, I'm never going to take this 3 and put it inside the sine and distribute it or something like that. That's crazy because this 3 is outside the sine function and this stuff is all inside the sine function. So what I'm going to do is the first thing I'm going to do is isolate the sine function. In other words, I'm going to undo all of the operations that happen outside of the sine function. Okay, so this is just regular equation solving and just looks a little bit hairier. So if I want to get this equation to look like sine blah 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 equals a number, the first thing that I want to do is get rid of this stuff over here. So the first thing I want to do is add 5, just like I would want to do if I had negative 5 plus 3x equals negative 0.3. If I wanted to isolate x, the first thing I would do is add 5 to get rid of this negative 5 here. So let's do that. Okay, plus 5, and I get 3 sine 90 theta minus 1.5 equals 2. And the next thing I want to do is divide by 3, divide by 3, divide by 3, sine 90 theta minus 1.5 equals 2/3. I'm going to write it as 2/3 and not as a decimal right now because um, I want to be exact. I don't want to round multiple times throughout my process. So if I write this down as negative or 0.67, then I rounded and I'm not going to have the accuracy that I want at the end of the problem. So we're really going to try not to round until the end whenever possible and use stored values in your calculator as appropriate. Okay, so at this line in the equation, I have sine of something equals 2/3, right? So what I have to do is I have to undo that sign. I want to think about what are the angles that have a sine of 2/3, and that is just arcsine, right? So if I undo the sign with arcsine and I get the argument of sine here, this part, 90 theta minus 1.5 is equal to arcsine of 2/3. Now, from this point on in this equation solving, there's a couple different strategies that you can use to get to the answer. And I'm going to show you the one that I like best, which is I'm just not going to evaluate arcsine right now. I'm just going to leave it written as arcsine of 2/3 and get to the point where I have an equation for theta. Theta is blah, blah, blah. And I'm going to evaluate arcsine at the end. You can evaluate arcsine now. I think that makes your equations get a little bit messier. You'll see what I mean when I get one as we go through this. But, you know, if you have a hard time understanding what's going on the way that I'm showing it, I can show you another way, or Mr. Gallagher can show you another way in class or outside of class. So what I'm going to do now is I'm going to look at this left-hand side of the equation, and I'm going to figure out how I can get theta by itself on the left-hand side of the equation. Okay, so the first thing I'm going to do, well, I'm just going to turn this conveniently into a divide bar, right, is divide by 90. Divide by 90. Theta minus 1.5. Now, I could leave this right-hand side written as arc sine 2/3 divided by 90, but I'm kind of lazy and I want to write it all on one line. So I'm going to write this instead as 1/90th arc sine 2/3, right? Because multiplying by 1/90th is the same thing as dividing by 90. And then all I have to do is add 1.5. That's easy. Plus 1.5. And I get theta is equal to 1/90th arc sine 2/3, arc sine 2/3 plus 1.5. Okay, so now what I need to do is evaluate arcsine, and I'm going to do it exactly the way that I did it in that video from 2 days ago, right? Arcsine of 2/3. I look at the unit circle, right, and I say, where is sine equal to 2/3? Sine is the v coordinate, so 2/3 is 2/3 of the way from 0 to 1, so it looks like there are 2 points on the unit circle, about here and about here, which have a sine of 2/3. I'm going to use my calculator to figure out one of those two values. Let's do that. Um, where did it go? TI. There we go. Okay, use my calculator to find one of them. So I want to make sure I'm in degree mode. There's lots of switching back and forth between modes these days, right? And I'm going to do inverse sine of 2/3. And that's going to give me one of the angles that has a sine of 2/3, 41.81 degrees. And that clearly is this angle, right? So 41.81 degrees. And all the angles at that location plus 360n. Okay, now I want to use symmetry to figure out what the angle is over here. So I can think about this as, this angle here, the reference angle, is also 41.81. So the angle, this angle, that goes from the standard position to that terminal ray is going to be 180 minus 41.81. I'm going to go ahead and do that on my calculator so that I don't have rounding. 180 minus the answer, okay, is 138.189. Okay, so I'm going to write that down just as 138.19 because I'm just going to retain those rounded values on my calculator, plus 360n, right? So the arcsine of 2/3 is 41.81 plus 360n and 138.19 plus 360n. Super. Okay, so now I just have to take those expressions and I'm going to put them into my equation for theta where arcsine shows up. Now the problem is I have two expressions, and that would be kind of weird to plug in this where it says arcsine there. So what I need to do is break up my equation into two sections. So I'm going to say theta is equal to 1/90th, and then the first equation, 41.81 plus 360n plus 1.5. And then I'm also going to solve, I don't have enough room, I'll move it in a second. So let's do this one first. So what I want to do, all I need to do now is simplify this equation on the right-hand side, right? So I'm going to distribute this 1/90th. I'm going to get theta is equal to 41.81 divided by 90. Okay, so I'm going to get that exact value back a second. I could have used this, stored this on my calculator, but I'm just going to recalculate it using inverse sine like this, right? Divided by 90 is 0.46456. 0.46456. And now I have to distribute this 190, 1 over 90 to 360 as well, right? So it goes to both of those. I'm actually distributing it. 360 divided by 90 is 4n plus 1.5. Now I'm just going to combine like terms. So I'm going to add 1.5 to the 0.46456. So plus 1.5. And I get 1.96456. Theta equals 1.96456 plus 4n. Okay, so that's half of my answers. Now I have to put the second half of the arcsine number in for arcsine. Let me see if I can get a little bit more room here. if I scroll down, it's not going to let me. That's super. Um, okay, I'm just going to cram it in. That's what we're going to do. Uh, so I'm also going to say theta is equal to 1/90th times 138.19 plus 360n plus 1.5. Right, so theta, distributing that 1 over 90 again, looking at my calculator. Um, 138.1896851 uh, divided by 90. 1.53544 1.53544 plus 4n plus 1.5. And then I'm just going to combine the 1.5 and the 1.53544, and I get theta equals 3.03544 plus 4n. So then all together, I have my general solution for theta. Combining these two, I say theta is equal to the set of 1.96456 plus 4n and 3.03544 plus 4n. Those are all the angles that make this equation true. That is not a short process. I want to just show you that graphically there is, this matches up as well, right? So if I look at where this graph is equal to -3, that's here, right? Do these answers that I got match up with what I see here? So if I let n equal to 0, right, I get my two angles are 1.9646. That looks like this, right? 1.9646 and 3.0355. That looks like this one. And then it says that every 4 units, I get that repeated. Now looking at this graph, where does 4 come from? 4 is the period of this graph, right? Oh, I didn't necessarily make it really clear what this graph is. I'm just graphing this function here, right? I'm graphing y equals the left-hand side of this function. I'm looking for where that function is equal to -3, right? The period of that is 4, right? So it makes sense that this point 4 units ago would give me this solution here, right? This is 1.9646 minus 4. And this point here is 3.03544 minus 4, okay? Great. We are going to, in class, show you guys how to check this on your calculator. Um, and make sure that your answers are right, not just graphically, but using some of the calculation functions on your calculator. There's a handout on that too. And that is all for today.